Good afternoon or good morning, everyone. Appreciate you guys being flexible. I had some stuff pop up in the afternoon, so just recording this early here. Hope everyone's enjoying the cold weather and Halloween coming up, and let's knock this out. So today we're going to be going over still in the pile capacity range, but now we're going to be going over the point bearing capacity. And I mentioned this last class, we're going over just multiple techniques to do so. And I'm going to share also on our Canvas page some of the engineering manuals for deep foundations where you can go through and see all the various techniques. We're just going to highlight a couple of them, two primary ones today. Okay, so let's see where we're at. Wrapping up the semester, already almost or more than halfway, almost 2/3 of the way through. Just as a reminder, we will have, or you do have the shallow foundation. So this homework not due Monday. That should be due this Friday or Sunday. Let me just check. You guys see it on Canvas. November 2nd. So yeah, this is due November 2nd. We will have a quiz posted after I post this class. That'll be due Friday on Halloween. And then this will be posted soon. Our last homework will also be posted. So right now we're still on track to have our exam during this take home time window from here and due on Sunday. Keep in mind too, next week we'll have class, but on the 11th, we do not have class because it is Veterans Day on a Tuesday for some reason, and they canceled classes that day. So after today, we're going to be primarily reviewing the point bearing capacity. So remember, when we were talking about pile design, we were talking about determining this capacity, which is in terms of a force or a load. So point bearing capacity is QP. Remember, if we're talking about total capacity of a pile, what usually we do is we say QU for ultimate. I'm just going to go ahead and put ULT for ultimate. This is equal to the point plus the skin friction or the sleeve friction. So last class we talked about this technique. I'll review that here in the next few slides. But now we're going to be discussing two techniques for point bearing. So the first one we're going to be doing is our good buddy Meyerhoff. And then the other one is going to be Vesich. One is very empirical, the other one is a little bit more analytical, and they both have limitations on the soil type that they're using as well. So these are what we're going to be reviewing today. Same resources here. I'm also going to be, I mentioned this earlier, but I'm going to be posting, or I already have posted, I'll put a link to it as well on our Canvas, the engineering manuals from Army Corps of Engineers from their design and pile foundations in 1991. It's a boring looking report that looks like it's from 1991 and it looks like the federal government made it, but so there's not pictures or anything, but it really does outline, it just takes patience reading it and going through each thing, but it does outline the design for the things that we're going to be talking about today. So as just a recap, remember, we're talking about ultimate pile capacity. I already kind of drew this picture here, but it's two mechanisms. We have the sleeve friction that is acting along the area or the perimeter of the pile. And so that's going to be acting, outside of just this cartoon, but this cumulative resistance called QS. And then we also have the QP, which forms from the point bearing resistance, which what we'll see follows very similar to a bearing capacity. It's just a deep bearing capacity. Now, the other thing to remember too is that this QS, the skin friction, this will mobilize or initiate the resistance sooner than QP. So for QP, this requires significant, or not a significant, but more settlement at the surface than you would see for the ultimate or for the sleeve friction, which essentially engages right off the bat. So the way we've found to estimate QS, or the sleeve friction, is by using an analytical technique that looks at the perimeter, the change in length, this effective or average earth pressure coefficient, the in situ vertical stress, and this is essentially right here, this gives us the horizontal, right? That's why they're multiplied by each other. And then this soil structure interaction, this friction angle here. Now, we said theoretically, we know that with depth, we should have an increase of effective stress. As we go further down along the length of the pile, the vertical effective stress will increase. Now, for the purpose of our design, though, to account for negative skin friction, or negative sleeve friction, we have this capping out at an L prime. And what I said last class was normally this L prime, or this distance, is about 15 times the base, or 15 times the diameter of the pile. You know, if it's a square pile, then we're talking about the base, or one of the dimensions. If it's a circular pile, then it's the diameter of it. And I'd mentioned that, I use these little squiggly equal lines here because this is approximation for it. And I'll show you from the engineering manual here where on the next slide, that it does change slightly based off of the soil type, but that 15 is in the middle. So the whole thing is we know the perimeter is staying the same. The change in length is just part of the math equation with the summation. We're assuming homogeneous material, which means that K is going to stay the same, that average K value here. And then the tangent of the soil structure interaction, that friction angle, is going to stay the same. So we keep all the constant things on the outside, and what's left is the summation. So essentially what we do is we draw the effective stress profile following this resistance, where from at the top of the pile to the critical length, or L prime, then we have this normal increase of vertical stress, or of in situ vertical stress. So this is normal. But then once we reach this L prime to the remainder of the length, we essentially have it capped. So we have that value capped at whatever this is. So we have this little piecewise function here that follows it. And the way I'm explaining it might be a little confusing. I suggest you guys also look at the Army Corps manual that I'm posting, and it kind of illustrates it a little bit easier. Now, a few things to note from this Army Corps here: they assume this critical depth, they use a D subscript C instead of L prime. Just note that's the same for us. So for us, they just use the variable DC, but for us, we use this L prime. And you can see here, this is the one that we said to use because it's for medium dense sands. That's primarily what we're going to have in Florida. If you have loose sands, then you use 10. If you have dense sands, then you'd use 20. And it kind of walks through it here, this frictional resistance, right? We saw something like this before. This is that effective stress, effective vertical stress. And it says, is it? Yeah, so the unit acting along the pile shaft may be determined by the following equation. So that's, again, showing that it's increasing normally. And then once we're at this DC is what they're calling it, then it caps out and it maxes here. So just wanted to show you, again, this might be referenced later, or something you might have to come across and be like, well, why is it 10 or 20? This is the reason why here. Okay, so all that to say, these are some of the other values, again, just recapping from the last class, in order to find these soil pile friction angles. And again, I'm not sharing the whole thing, but if you go back to this manual that's in our Canvas group now, I think it's in the manual section on our Canvas page, then you'll see all of these values too here. Then they go into a little bit more in-depth details of all these frictional resistance and the K values to use and all that stuff. So that's QS. Let's talk about the point bearing resistance, QP. So recall from the shallow foundations, Terzagh's equation, we have the shallow foundation bearing capacity of the soil component of three parts: the cohesion, the surcharge, and then the unit weight. Now, there's a similar failure mechanism from piles. All it is just deeper. So really what we're saying is that this point bearing, in order for this point bearing to fail, it will form this wedge, and then eventually it'll form a shear pattern acting to the left or to the right of it. So it's a similar mechanism, just deeper. So for a singular pile, what we could say is, okay, this ultimate is equal to the point bearing. And, we know that the point or the factors are going to change a little bit. But we'll just say, following the same mechanism as Terzaghi, that it's part of these three contributing factors: cohesion, surcharge, and the soil unit weight. Now, keep in mind here with this, now we're talking about the pile diameter here, where before we were talking about the footing width. Now, if these two terms are staying the same, and the unit weights are the same, and these factors are somewhat similar, we're assuming that this pile diameter, or not even assuming, it's probably self-explanatory, this pile diameter or pile width is going to be much, much smaller than a typical footing contribution, right? Footing contributions can be like 5 feet, 6 feet, 7 feet. These pile diameters can be relatively small for these like 1 foot, 2 foot kind of things, unless we're talking about some of these larger designs. So therefore, with that, we're going to say that this term is pretty negligible. So this term here, just because of that, the D being a smaller size, this is going to go to 0. So that diameter of the pile is going to be 0. So what that means is, okay, we're going to simplify this now as the point bearing capacity of this being cohesion plus the soil surcharge. Now remember, with this soil surcharge, we're now talking about this whole depth here, where this is the unit weight times this LB. So of course, though, with this as a lowercase and being Terzaghi, remember that this produces a stress. And what we need here is a force. So we need to remember that, stress is equal to force divided by area. So really, we don't need lowercase qp, we need uppercase q, which is going to equal lowercase times the area of the pile. So this is how we derive it. This is the assumption made. Okay, this is going to be the stress term, but then we need to plug this in to here to get the actual capacity term for the pile. And that's what we'll see here on the next slide here. So this point bearing QP, this is the force. This is equal to the area of the pile times the point bearing capacity of the pile. And then just plugging in what we just had before. Area of the pile, again, easy to calculate. This is C times N. This point bearing capacity, I'm putting a little asterisk just to denote that it's different than the shallow foundation ones. And where the area, AP is the area of the pile, C is cohesion of the supporting of the tip. It's important. This is going to be all the soil properties around the tip. The Q prime is the effective vertical stress at the level of the pile tip, again, shown here. And then these N subscript C and N subscript Q is going to be the bearing capacity factors for the pile. And essentially with these here, these are the techniques to find these. So the techniques to find these, this is where we have our like Meyerhof technique, our Vesich, our Coyle Castillo, all the different like giants in the pile design area, they all have these. Now, the important thing to note too with this is this AP, this area of the pile, a lot of times we would have the effect or the total area, cross-sectional area of the pile. Because what we assume is when we're driving, especially if it's a hollow pile or if it's a steel pile, we're eventually going to have this soil plugged by the time it's being driven into the soil. Now, if it's a bored pile for some reason, this might not be the case. Or if it's a pushed pile, it might not be the case. But a lot of times we would assume this. So the total area of the pile would be this area of the steel plus the soil plug around it. So let's talk about a technique in sands only. Another way of saying this is we have a cohesionless soil. So if we have a cohesionless soil, cohesionless, that means there is no cohesion term. So this cohesion factor is going to be 0. So if we think back to our point bearing capacity equation for piles that we just had before, again, just kind of being redundant here. Let me just draw this out. So if we have an equation like this, but this C is equal to 0, then of course this whole term goes poof, that first term. So we have a much simpler term here, this AP times Q prime times NQ, right? Because that C prime goes 0. And so this is one of the ways that Meyerhoff, our good buddy, 1976, decided, look at him, you can trust him. It's just a man with his dog, and the most American man ever out there. Anyways, the point bearing capacity of pile in the sand, it will generally increase with a depth of an embankment in the bearing stratum, but reaches a maximum value at an embankment ratio of LB over the diameter of the pile. Now, in a homogeneous sand, LB is actually the embedment length of the pile. So this is that bearing length. That's what we need to say. So if the pile has penetrated into a bearing stratum, like let's say you have like organic material at the top or something, then that bearing stratum will be less than the total length of the pile. So keep that in mind. So homogeneous sand, we're golden. The LB, the bearing length, is actually the embedment length. But if it's into a weaker soil, we neglect that weaker soil. Now, beyond this critical embedment ratio of LB divided by D, the value of this point bearing stress remains constant, very similar to the frictional resistance remaining constant. So this is what we call like a limiting or maximum, a limiting point resistance. So that's this QL, it looks like QI, but this is limiting point resistance. So all that to say is eventually, again, like if we have a pile that is an infinitely long pile, eventually this Q term is going to maximize or is going to max. And this Q term, which is a contribution to the total resistance here, this will eventually max at this ratio, this LB divided by D. So you don't get just infinite amount of strength. So that's why in Meyerhoff's method, which is I'm going to show right here, we have to calculate two things and then pick the smallest. So yes, we are going to follow the equation as shown before. So we would calculate this as is area of the pile times Q prime, which is the vertical effective stress at the tip of the pile. But what we also do is we check and see which one is smallest, either this AP versus the limiting point resistance. And this limiting point resistance follows this equation here. So again, this is cohesionless, so it's equal to 0. So that's why that term is out. But what this whole thing is telling us is we would pick the smallest for the design. So it's very similar to what we were just talking about with the frictional resistance. If we were to plot this point bearing resistance versus the embedment depth, the embedment length divided by the diameter, so normalized with the diameter of the pile, we would see it increasing to a certain extent, and then eventually we would see that value maximize. Now this is occurring at some critical value. Some critical, CR for critical. But at this point here, this is where our QP is equal to the QL. So the critical ratio is found through this technique here. So by calculating this, we can actually find this critical embedment ratio, which is sometimes used for design, this critical embedment ratio, LB divided by D. So remember, keep in mind up here, this is the big thing here. If we have sand, then most of the time LB is going to be equal to L. We only would use this where the embedment ratio might be less if we neglect a soil layer, like if there's organics at the surface or even like a softer sand or something. So that if that LB is smaller, then we should have a more conservative design. So the question is, all right, what is this NQ here, this bearing capacity factor? And so we find this very similarly to how we would use it for the shallow foundations in Terzaghi and the Ashto method. So use, it's predetermined based off of the soil friction angle, or it's a function of that, I should say. So this is the chart you can use. Keep in mind the scale here on the y-axis for NQ, the soil friction angle. Again, reading it, like let's say we have a value of 30. Read this up and then read it over, or you can, use the table here too to get a little bit more accurate estimation. So this, again, just to summarize, this is that QP is equal to this equation here, or QP is equal to this atmospheric pressure times the tangent of the friction angle of the sands. And you would pick the smallest for the design. So pretty straightforward, and it does follow a similar methodology to the skin friction, except you're not doing it by the perimeter of the pile, you're doing the area of the pile, because that's what's loading. So this is in sands. Now Meyerhoff developed a similar method for clays. So this is cohesive soils, or what we would call frictionless soils. So in this case, the friction angle is equal to 0. And we have cohesion controlling. So as before, the original method, again, redundant, so just put 2x or whatever if you haven't already for this part, but I'm just going to write it out anyways. Again, the initial theory, knowing that it's these two combining forces. If it's a frictionless soil, then what we have is only the cohesion term. Like this. Why? Because this is a function of our friction angle. And if you look back here, well, yeah. If you look back here, when the soil friction is 0, then this is going to be 1. And so the value here is very small. So it doesn't contribute much at all. So with this technique, let me go back real quick. So in clays, the mechanism is a little bit harder. So what Meyerhoff did was use an old, well, not an old, but empirical data to create this relationship here where we say, all right, QP is going to be about equivalent to 9 times this Cu, which is not necessarily cohesion, but instead this Cu is called the undrained cohesion. So undrained cohesion. So Cu is what we call undrained cohesion, which for frictionless soils is also equal to this thing called Su, which is the undrained shear strength. So this goes back to like our triax test, thinking about this. When we were talking about, okay, let's say we're plotting a triaxial test on a clay that has no friction, which means the friction angle is 0, and which also means that if it is undrained, the pore water pressure cannot dissipate. So if we were to do different tests and actually calculate a failure ratio, then we would see that this friction angle is 0. There's no angle to it. So what that does equate to is a consistent cohesion, which is that undrained cohesion. And so what we would see is that these circles would therefore be the same. So this change in deviator stress, this is what we call I'm just going to say UCS, but unconfined compression strength. So this is unconfined compressive strength of the clay, or UCS test. So that Cu is equal to UCS divided by 2, right? Because this is just a diameter and this is a radius. So that's how we can get that there. So this method is an empirical method. So it's for estimates. What you'll see next class, we'll talk in a little bit more details about it. This for clays, it really is good to use some type of in situ testing to get a better understanding of it. So those are Meyerhoff's methods. What I want to do is do the same thing for another additional method by Vesich. So Vesich, let's go. Where's this? So Vesich, this is first Sands. Look, he looks a little bit scared. He's not hanging out with a nice Labrador retriever. He's from Serbia. Serbia back then was a rougher time than the good old USA in the 50s. So this is a cohesionless material, which means, again, the cohesion aspect is going to go to 0. Now, this is proposed based off of a really interesting theory, and this theory is called the expansion of cavities. Not a dentist term. It's very similar to like Boussinesq, where we were saying how stress can redistribute through a media. But now it's talking about, well, how does the void space redistribute through the media, not at just the stress? So this is really important theory in driven piles. And the important thing with this is we use effective stress parameters or at-rest earth pressures. So although the equation looks similar, where we have this QP, this point-bearing force, is equal to the area of the pile times the point-bearing resistance of the soil. This area of the pile is the same, but now this QP is equal to this effective stress term and then times a bearing capacity factor, but this is a new bearing capacity factor. This is a stress subscript. Now, there's 2 terms here. This is the mean effective normal ground stress at the level of the pile point. So that's what this bar is right here. And the way we calculate this is this weird weighted average looking thing where we have 1 plus 2 times the at-rest earth pressure coefficient divided by 3, and then times Q prime, which is the, again, same as before, it's the point, the effective stress at the pile tip. The length of the pile, that. So the effective stress at the pile tip. Now we use at-rest earth pressure coefficients, which is important to go back and recall that that is K naught is equal to 1 minus the sine of the friction angle. Now, the other thing we have is this bearing capacity factor, and this is where the expansion of cavities theory comes in. So this is a function of this really lovely term that we're going to try to simplify, but this is called a rigidity index, or IRR. Now, in Bess's method, this reduced rigidity index follows this form, which if you're going to reduce something, you have to first know what the initial thing is. So the initial rigidity index is a function of the Young's modulus and the Poisson's ratio, the friction angle, and then again, that effective stress right here. At pile tip. So this little delta term too, which always frustrates me that they just use a standard delta here. This is the average volumetric strain in a plastic shear zone before the point of the pile. So what the heck does that mean? Oh, it's okay. I'll give you an equation here in a second. The Young's modulus, what we can use as a correlation for this based off of the type of sand that we use. So just very generalized. So we'll say like, okay, use a 100 to 200 for loose sands, and then 200 to 500 for medium dense, and then 500 to 1,000 for dense. So picking a spot in between for the Young's modulus, and then just making sure it's in the correct units. So that's what that PA is there. That's the atmospheric pressure. That's really just to get it in whatever units you're using your Young's modulus in. The Poisson's ratio, if you can do that test, like an actual find the Poisson's ratio, then you can, that's great. This is a good empirical correlation from the friction angle. I mean, good to a certain extent. Obviously, it has to be a high enough friction soil. If it's lower than 25, then you're not getting this. So this is for like a medium to dense sand. And then that volumetric strain in the plastics, this delta term, is a function of friction angle and the vertical effective stress, again, at the pile tip. So Q prime, another way of writing this would be the length of the pile times that submerged unit weight, or whatever is, if there's groundwater table, just to make sure that it's effective stress conditions. Now with these two, these are all empirical. That's why they look like they're just weird looking equations. So again, they're estimates based off of the data that was used to train these. So take that for what it is. And that's why like being conservative, and when we'll talk about it here at the end of this lecture, the factors of safeties are important. Now, the cool thing with this is this delta and the IR, this can actually be measured of the soil. I'm going to put in parentheses because it's more like correlated from the cone penetration test. So if you're driving piles in sands, I would always suggest trying to get a CPT out there, because that CPT really is essentially the same mechanism of failure for driving that pile. You're essentially driving a scaled pile into the ground. So these rigidity indexes and the average volumetric strain in this shear zone during failure is determined from the CPT, and there's some good correlations out there instead of just these kind of high level estimates of friction angle. So this is all to find, again, this is the whole reason I'm saying all of this is because this function here, this bearing capacity factor, this is a function of this reduced rigidity index. And so the table is right here. So this is the bearing capacity factor using Vestige's 1977 technique. Again, all for the purpose of this term here. So this, we would calculate or estimate the reduced rigidity index, and it's based off the friction angle, and then you would find the corresponding one for this. What you see is that this is from Synthesis of Highway Practice by American Association of State Highway and Transportation Officials, which is AASHTO. So AASHTO does use this and has essentially, like, they were the ones who initially started this. So for piles design or driven pile design in sand, this is what you would use in for highway structures and roadway structures. Remember, this whole thing, type right up in here. So this is for sands only. Don't get it confused here. This is, again, only sandy material. For frictionless or clay material, again, assuming that the friction angle goes to 0, we see a similar form. But this QP is going to be similar to Meyerhoff's. It's going to be an undrained shear strength or undrained cohesion. And then this cohesion bearing capacity term. Again, the CU, same term as before, undrained cohesion, which is found from the undrained shear strength or estimated. And so when that friction angle is equal to 0 for this term, if we look at the thing from the previous slide, let's go here. Essentially what we do is we use this term, extrapolating this up to go to 0. So it's a different table, but we can find it using this equation, but of course it's probably a lot easier. We'd still find the rigidity index with these values at 0 for the friction angle. So we'll make sure that our Poisson's ratio is corresponding, and make sure that our volumetric strain, the delta, is corresponding, and the reduced rigidity index follows it correctly when it comes to 0. And then we can find, when friction angle is 0, then we can find the IRR from slide 17 or whatever was before. Yeah, slide 17. And then we can estimate the bearing capacity factor that way. Now, what this also assumes is that when clay, this is assuming saturated clays, which means there's no volume change when it's loaded. Now, if you remember back from mechanics of material, no volume change means the Poisson's ratio is 0.5. Just as a recap again, like let's say we have this like little square and we load this square, we're going to see a deformation in this direction, but we'll see an equal and opposite deformation in the other direction, which means the total volume change is equal to 0. And if we have that case, then that means the Poisson's ratio is equal to 5 or 0.5, which is the max, because whatever is happening here, this lateral or axial strain, half of it is occurring here, 0.5 of the lateral strain. So that's where that's coming from again. Now, if we have this no volume change, then this means the strain average is equal to 0, because that is offsetting. The strain in one direction is equal to the strain in the other direction. So that average volumetric strain is 0, because we have a positive strain and a negative strain. So it equals 0 for that case. So this makes the calculations a little bit easier too when you're finding your reduced rigidity index. So all that to say, what we can actually do is simplify this. Is the reduced rigidity index is actually equal to the normal rigidity index which is estimated using this 3 times the undrained shear strength. So these are estimates based off of the primary soil type, whether you have sands or clays. Now, of course, with shallow foundations, especially with this, we have geotech stuff, which means we're using natural material or geomaterial, which means there's variability, which means we always need to apply a factor of safety. And especially here where we're also peppering in some theory and assuming that this theory of mechanism is consistent through everything. So with this, we always need to apply a factor of safety similarly to shallow foundations, which means we'd have to consider what the actual strength or the capacity is, and then what we're actually going to allow to happen or allow to load. So the other way of saying this is, okay, what is the capacity versus the allowable? And so this is how we get the estimates of Q allowable, similarly to the factor of safety for shallow foundation. So we take our Q ultimate and we divide it by, or we reduce it by the factor of safety. Now remember though, this Q at U is really equal to QS plus QP divided by the factor of safety. Now, in the reference manual for the Army Corps of Engineers that I posted, this is just a nicer looking slide, but simply it's pretty much the same. These are some of the, suggested factor of safety or minimum factors of safety. And you can see for in compression and in tension, they might vary based off of the method of determining or verifying the pile. So even if we are using a pile load test, so verified using a pile load test, what we still have to have a minimum factor of safety that is pretty high. So 1.15 to 2. And you can see if we have not verified by load test, which I don't know anybody who actually does non-verified, then these are minimum factors of safety. So essentially like max values or something. You would need to make sure that anywhere between 3, like something higher, is used there, which means we're taking the the ultimate, what we're calculating, and dividing it by 3, and then saying, all right, this is what we can maximize when it comes to it. So next class, we'll talk about subsurface testing correlations, and we'll also go over pile load tests. So keep that in mind. And then also remember, please do the quiz this week on the 2 lectures from today and on Tuesday. And then also don't forget you have your homework for shallow foundations due next week. So please submit that on time too. Thank you guys.